Hi there, this is Manuel with Entagma, and I'm here with a new Geometry Nodes tutorial. Geometry Nodes offers a node to distribute points on surfaces, but it is lacking a node to distribute points inside of an object's volume. So that is what I want to create today, a component with geometry nodes that scatters points inside of objects. So let's dive in and get started. First, let's get rid of everything, and I usually create just a plane to hold the geometry node setup. Call it distribute. And now we need a Geometry Nodes viewport, switch this over to Geometry Nodes editor and create a new setup and call this distribute2. Now that we have that, let's create an object that we want to use to scatter points inside. I want to use a torus for this, so let's create a torus and make sure that it is a little thicker, 0.5, minor radius, give it more subdivisions. 24 like this. So that will be our dummy object. Go to distribute again and drag the torus inside of the graph. And now you can make the torus invisible. So this is the object that we want to use. Let's connect it here to see if it is working, and it is. First, we want to create a grid of points that packs these points tightly. We will create this in a cubic fashion, and we want to make sure that it is larger than the object. And then we want to implement a test to see if a point lies inside of the torus or outside, and all the points that lie outside will be deleted. So the first thing that we will need is the bounding box of the torus. So let's create a bounding box. And now let's measure the extent by creating a vector mass, setting this to subtract, and then just subtracting the min from the max. This gives the vector that is diagonal inside of this bounding box cube. And now let's split this apart by separate xyz. And now that we have the dimensions, we can determine how many points to create for the individual axes. But there's one value that we need to know before we can calculate this, and that is the point separation, or the size of the points. Let's create a value node for now. Value, go to node and call this point size to remember what this is for, and set it to 0.1 for now. Okay, now we know how large the box is and how large the points are. That means that we can calculate the point count. First, let's do it for x. Lay down another mass node and set it to divide. And now let's use the x dimension and divide it by the point separation. Let's see what this gives. Create a new viewport over there and switch this to spreadsheet. And now we can create a viewer node, like so. Connect the geometry to the viewer node, connect this value to this value here. Let's switch this over to viewer node, and now it shows 30. That means we have 30 points in x to be distributed. But what if we have a more irregular value, like 0. something? Now we have an irregular number here, and that is not nice because the point count always has to be integer. That is why we want to append another node to round this off, and we want to switch this to seal. Go back to 0.1, 30 again. But there's one more thing that we want to do, and that is to add 1 to this number. So duplicate this node, set it to add, and just add a value of 1 here. So now we have 31 points. Now I want to take these 3 nodes, select them all, and press Shift W for the Node Wrangler add-on, and say frame selected, tick off the color, and call this count_x. Just to make sure to remember what this is for. Now let's create the actual points. For this we want to lay down a mesh line and set it to offset. And we want to connect this value to the count. Now this creates a mesh line with 30 points. Connect it to the viewer and connect it to the output. So let's move the output over and connect the mesh line to the output. What is the correct offset? The correct offset is the point size that we have here. So let's create a combine xyz, because the offset is a vector quantity, and we only want to set the offset in x. So now connect this value to x. And we get a line that is exactly the size of the bounding box. For visualization purposes, we can drop another node, and that is called mesh to points, just to convert these vertices into a point cloud, because this point cloud is easier to see. Now that we created the points for x, let's do the same thing for y. What we want to create is a mesh line that we will use to instance this line onto to create a two-dimensional grid of points. It is not as straightforward as the x case because the distances are different. We cannot just use this point size here because we want to achieve a very tight packing of the points. So let's think about this for a second. If I have a point here, and then in x the next point touching the first one and then the next one, if I now want to extend this to y, I don't want to put my next point here, because that would leave gaps. Instead, it is probably a good idea to put the next point here in the gaps, like so. And then with the next row, we will have the old distribution again. So if you look at this structure closely, you can quickly figure out that the points are distributed in a triangle, an equilateral triangle to be precise, because the sides of an equilateral triangle are always the same length, and that means that the points are the same distance from each other. That is exactly what we want to achieve. But that means that while we have a distance of a here in the x direction, we don't have a distance of a here in the y direction. Instead, we want to use the height of this triangle to figure out how far to offset the y. Let me quickly create a new layer of annotations with a different color here. So we are interested in this quantity, the height of the equilateral triangle. And by using the Pythagorean theorem, we can easily figure out the formula for this height. The height of this triangle is the square root of 3 divided by 2 times a times the length of one of the sides. So instead of having an offset of a, we now use an offset of h. Let's implement this first. Turn our point size here into the height. Let's introduce a new math node, mass, and switch this to square root. And this should be the square root of 3. And now we want to divide this by 2 by duplicating the node. Set it to divide by 2. Last but not least, we want to multiply this by a, another math node. This time we want to multiply, and we want to multiply by the point size. So these three nodes now calculate h. Let's again select these three, press Shift W, frame selected, and let's just name this tree height. Now that we have our new offset value for y, we can use these three nodes and duplicate them. And let's remove them from the frame to calculate how many points we will have in y. So this time we want to divide the extent of our bounding box in y by the height we just calculated, like so. And that gives the offset for our y distribution. And now we can do the same thing as before. We can create a mesh line and connect our count here. Don't forget to put this in a new frame. And let's call this one count y. Like so, new mesh line, and now we want to specify the offset for this mesh line. For this we will need another combine xyz, but this time we don't want to use x, instead we want to use y, and we don't want to use the point size, instead we want to use the tree height. Like so, so connect it here and specify the offset, and if we just quickly connect this to our mesh to points, you see that is what we get. And we get more points. If we connect the count temporarily to the value, we see we get 36 points because the distance is different. Now with these two lines in place, the x and the y, we can create an instance on points, and we can use the y line to instance on, and we want to instance the x line. Now let's see what this gives, and it gives a regular grid that is roughly 3 units in each dimension, exactly like the bounding box. Although we now calculated the right height, we do not have an offset yet. We want to offset every odd row a little bit to make the packing perfect. So let's have a look at our diagram again. How much do we want to offset this? From the drawing we can see that we want to offset by half of a, so a divided by 2. Let's go over here, and we want to offset every odd line. So first, let's introduce a set position node, because we want to alter the positions of every odd point on this mesh line in y. And now we need a selection, because we only want to affect the odd points. To find the odd points, let's drop an index node, and then connect the index to a new math node, set to modulo. Switch this to modulo 2. Now if we connect the index, we will get a value of 0, 1, 0, 1, 0, 1. So every second point has a value of 1. And now we can test by comparing. We can test if this value is 1, equal 1. And let's use this as a selection for the set position. Let's quickly see what this gives, and you can see now we can just alter every odd row. 0 again. Now that we did this selection, we just have to take A, so the point size, and with another math node, divide it by 2. Divide this by 2. Let me get rid of the N panel to get more space here for me. So this is the value that we want to use as an offset, and we need another combine XYZ. Because this is again a vector quantity, we want to move in X direction and connect this to the offset. And as you can see, this works. Now that we have this perfectly fitted grid, we can care about the Z direction. Before we create just another mesh line and another instance on points, let's think about how much we want to offset the points in Z. So while we have triangles in the plane, if we think about the three-dimensional structure, we will have 1 point here and then 1 point there and then 1 point there, forming this triangle. But then three-dimensionally, the next point above these should go here in the middle. So it is the tip of a little pyramid. So what we will have here is a tetrahedron. And the point above the first plane is the tip of this tetrahedron. So to figure out how far to offset this, we have to figure out the height of the tetrahedron. If I draw this bigger, so we have the triangle here, and then the triangle midpoint here. And above the triangle midpoint, we have this point here, which is the tip of the tetrahedron. What we want to calculate is this, the height of the tetrahedron. I call it HT. That is the offset in Z. How can we calculate the height of the tetrahedron? Well, we can just look it up online, and it turns out that the height of the tetrahedron HT is the square root of 6 divided by 3 times A, one of the sides. That is the quantity that we want to calculate for the Z offset. So let's do just that. Let's move this over. We need another math node. Math, again set to square root, but in this case square root of 6. Then we want to duplicate this node. Let's move this further down. We want to duplicate this node, and in this case we want to divide by 3. And then a last math node, multiply all of this by A. And A is the quantity up here, our point size, like so. So this is the height of the tetrahedron. Let's frame it, frame selected, and let's call this tet height. Remove the color. So that is our tetrahedron height. And now with this in place, we can calculate how many points we need in Z by duplicating these 3 nodes, removing them from the frame, moving them down there, reframing them, and calling them count underscore Z. And the count underscore Z will use the Z value of our bounding box vector divided by the tet height. And that gives how many points in Z we need. Now, the same story as before. We will need another mesh line. So let's duplicate this one. And this mesh line gets the count in Z. And as an offset, let's duplicate this combine XYZ node. It will use the tet height in Z. That is the offset. So let's see what this gives by temporarily connecting this here. And this gives only 4 points. That cannot be correct. We must have an error here. Oh yeah, switching this node over to divide, reset the value to 0.5. So let's do 3 again. So that looks more like it. Now we have a third line that we can use to instance the planes on. And we can do that by using another instance on points. For this instance on point, we want to use the newly created Z line for the points to instance on, and the planes we created earlier as instances. Like so. Let's move this over, connect the mesh here, and you see now we get a box made out of points. But although the points are the correct offset in Z, they are not moved over. They are just above each other. But they have to be moved over in X and in Y to be at the center of the pyramid. To move them over, we again can just create a set position, put it here, and we can duplicate this structure here with the modulo, because again we just want to move over every odd row or every odd point. So let's connect this to the selection as we did before. Let's see if it works. Yes, now we can move every odd plane, but now we have to figure out the offset. So back to the diagram. Last time. By looking at this diagram, we see that the tip of the tetrahedron is exactly above the center of this triangle. So we have to figure out the center of the triangle. Let me quickly draw the triangle again. This is our triangle. What we need is the center point. This point here. The center C. Let's call this quantity H1 and this one H2. By looking this up online again, we can figure out that H1 is exactly 1/3 H. And H2, by the way, is 2/3 H. So this midpoint divides the height of the triangle with a ratio of 2:1. If we take the height and divide it by 3, we get this H1 here. And that is our offset in Y for the planes. Then the offset in X is again half of A. Half of A in X and H1 in Y gives the center point here. So let's implement this. For this we will need another combine X, Y, Z, because offset is a vector quantity. In X we want to offset half of A. We already calculated this before. Here, divide by 2. So that is our offset in X. And now we want to take the height and divide it by 3. Let's use a new math node. Let's duplicate this one. It's already set to divide. In this case we want to divide by 3. And now let's find our height. Where's our height? Here's the tree height. And let's divide the tree height by 3. That is H1. Now let's use this for the Y offset. And now you see that we have a perfect packing of little dots. Let's quickly check if this is working by putting actual spheres onto the points. So now, just for checking, let's create another instance on points. And let's use a sphere, icosphere, as an instance. Like so. Of course, the icosphere is far too large because it should be exactly 0.1. So let's go down with the radius to 0.1. And let's up the subdivisions to 3. And of course, this radius is too large because the value is the separation, so the distance between 2 points, and the radius is only half of this. So let's go down to 0.05, which is half of this. And you can see now we have a block of perfectly packed spheres. So this part is working. We have now a bounding box filled with spheres that are barely touching. The next step is to move this over and then find a measure to select only the points that are inside of the torus. So now we have a box of points, but it is not at the right place. The bounding box does not start at the origin like our box does, so we have to transform it over. So let's append another transform node, transform, to transform what we created. And where do we want to transform it to? Well, at the minimum corner of the bounding box. And the minimum corner of the bounding box is here. So let's put this minimum into the transform over there, and that makes our point grid jump to the location of the bounding box. Now it is exactly where it is supposed to be. Now for testing if the points are actually inside of the torus. Before we implement this test, let's think about it first. We have a torus, like so, and then we have points inside of the torus, or here, and we have points outside of the torus. How could we test if the points are inside or outside? My method goes like this. First, for every point, we will find the closest point on the surface of the torus. So in this case, that will be this point, and in this case, that will be this point, and in this case, that will be this point here. Then we will calculate the vector between the point and the closest point, with the closest point as a tip, and that will give us these vectors here. And you see, the vectors of the points inside of the torus point outwards, while the vectors of the points outside of the torus point inwards. Now we just have to compare these vectors to the normals on the surface of the torus to see if they point in the same direction. And if they do, the points are inside of the torus. If they do not, they are outside. Let me indicate this. Not only do we want to find the closest point, but at this point we want to find the normal of the torus. Like so. And then we need to test if this normal vector is pointing in the same direction as the difference vector. This can be achieved by using the dot product, because the dot product is a measure of similarity between vectors. So by using the dot product, we can tell if these vectors point in the same direction as the normals, and if they do, the points are inside, and if they do not, the points are outside. That is what I want to use to decide if I want to delete points or not. So let's implement this. First, we want to introduce a delete geometry node, delete geometry. But before we use the delete geometry, we probably want to convert the instances to real geometry. So move all of this over and create a realize instances to turn all of this into real points, and now append this delete geometry. And immediately everything vanishes because the selection defaults to 1 and everything is selected, everything is deleted. We want the position of our points. So let's get a position. The position of our points. And now we want to find the closest point on the torus. For this we can use a geometry proximity, and we can use the position of the points as the source position. And the target geometry for this geometry proximity is the torus. I could use this torus node here, but it is very far away. So instead I would just drag the torus again into the network, works too, and connect it here. So now this spits out the position closest on the surface of the torus to each and every point that we have in our grid. Now let's form the vector between our current position and the position closest on the torus by using a vector math. And let me quickly hide these annotation layers. We want to go with the closest position first and then the position that we have. And this gives the vector between our position and the position on the surface. The next thing that we need is the normal at the closest position. And to find this, we need another node, a transfer attribute node. And this should not transfer a float, but a vector. And the vector we want to transfer is the normal. So let's connect the normal to the attribute, and the geometry we want to transfer the attribute from is again the torus. So the last thing missing is a source position, and this source position is the position closest to the points. So the position we found here. This setup looks the normal up at the position that we find with the geometry proximity. We can use this to do another vector math operation, duplicate this vector math node and set it to dot product. We want to find the dot product between this vector and the normal. And now we can just see if the dot product is negative or positive to decide if the vectors are pointing in the same direction roughly or in different directions. So that means we can use another compare, and we want to set this to less than or equal, and we want to compare if this quantity, the dot product, is less than or equal than 0. And if so, we want to delete the geometry. So this result goes into this selection. I get this blob. Obviously I did something wrong. Of course, I forgot to switch this node from add to subtract. It should be the vector between the position and the closest position. And of course I want to use less than or equal here. And if I do that, now it deletes everything that is outside of the torus, leaving us with a torus made from tightly packed points. And this concludes how you create a component that scatters points inside of an object's volume.
If you like what we are doing, please consider becoming a Patreon.
for supporting us and for access to more in-depth courses on topics like volume techniques or PDG or Vellum and more. To everybody who is already supporting us, thank you so much. Without your continuous support, Entangma would not be possible.